Welcome back, everyone. Today, we are exploring working with real numbers. In this unit, we cover several core areas including sets and expressions, the real number system, exponents, roots, fractions, and mathematical logic. For today's lesson, we are going to focus entirely on our second topic, the real number system. Let's dive in. The real number system is based on simple rules. It relies on the existence of a set of numbers plus two binary operations. In Algebra 1, the set of numbers used is the real numbers, denoted by R, and the two binary operations are addition and multiplication. Next, let's explore the properties of equality that always hold true for any real numbers A, B, and C. First, we have the reflexive property, which states that it equals A. Second, the symmetric property means if it equals B, then B equals A. Finally, the transitive property states that if it equals B and B equals C, then it equals C. Think of a binary operation like a magic blender. You put two separate ingredients inside, and it combines them to create one brand new dish. Now, let's look at equality. The reflexive property is like looking into a mirror. An object always looks exactly like itself, just as A always equals A. The symmetric property is like a perfectly balanced seesaw. If the left side is equal to the right side, we can swap their places, and it still stays perfectly balanced. Finally, the transitive property is like a chain reaction. If block A connects to block B, and block B connects to block C, then block A is automatically connected to block C. Let's try a practice problem together. Look at the statements on the screen. If x equals y and y equals 5, then x equals 5. Can you identify which property of equality is being used here? Take a look. Now, let's look at the solution. This is a classic example of a chain reaction. Since x connects to y and y connects to 5, x is automatically connected to 5. Therefore, the correct answer is the transitive property of equality. Addition and multiplication are binary operations because they require two inputs to produce a third number. A set of numbers is said to be closed under a given operation if, when you perform that operation on any two members of the set, the result is also a member of that same set. The set of real numbers, R, is closed under both addition and multiplication. Adding and multiplying real numbers always produces other real numbers. Mathematically, if A and B belong to the real numbers, then a plus B and a times B must also belong to the real numbers. Imagine a magical island called the Real Number Island. No matter who you add or multiply inside this island, the result can never escape. It is trapped, meaning the final answer is always forced to stay on the same island. Let's look at a concrete example using real numbers. Take -3 and +5. Since both are real numbers, their sum, 2, is a real number. And their product, -15, is also a real number. This proves closure. Here is another practice problem. Consider the set of all odd numbers. Is the set of odd numbers closed under addition? Think about what happens when you choose any two odd numbers and add them together. Let's find out. Let's look at the answer. The correct choice is B. It is not closed. To prove this, we can find a counterexample. Let's take two odd numbers, 3 and 5. When we add 3 and 5, the result is 8. Since 8 is an even number, it escapes this set of odd numbers. Let's learn about the substitution principle, also known as the substitution property. For any real numbers a and b, the number a may be substituted for the number b if it equals b. This means that if two expressions have the same value, one expression can be written instead of the other. Let's look at some examples. For instance, the number 35 has the exact same value as 20 plus 15, or 30 plus 5. Therefore, 35 can be replaced by these expressions. Similarly, the expression 4 times 8 can be replaced with its exact value, 32. Think of the substitution principle like a money exchange at a store. A single $10 bill and two $5 bills look completely different. However, because their total value is exactly equal, you can freely substitute one for the other at the cash register. Let's test our understanding with a quiz. Evaluate the algebraic expression 3x plus 5, given that x is equal to 4. Use the substitution principle to find the final value. Let's see how it works. Here is the solution. By the substitution principle, since x equals 4, we can replace the variable x with the number 4. This turns the expression into 3 times 4 plus 5. 3 times 4 is 12, and 12 plus 5 gives us 17. In the real number system, 0 is the additive identity because adding it to any number does not change its value. Similarly, 1 is the multiplicative identity because multiplying any number by 1 leaves the number unchanged. Every real number has an additive inverse, which is its negative. When you add a number to its additive inverse, the result is always 0, the additive identity. For instance, the inverse of negative m is positive m. Think of identity elements as a magic mirror. No matter what number looks into it, the number stays exactly the same. In addition, 0 acts as this mirror because adding 0 leaves the number unchanged. In multiplication, 1 is the mirror because multiplying by 1 gives the exact same number. Now, think of the additive inverse as a perfect seesaw. Every number has an exact opposite partner that completely cancels it out, bringing the seesaw back to perfect balance, which is 0. For example, positive m and negative m cancel each other out to make 0. Let's test your understanding with a quick quiz. Find the unknown value x in the following equation. Negative 7 plus x equals 0. Think about what property we should use here. Let's see how it works. Here is the solution. When we add a number to its additive inverse, the result is always 0, which is the additive identity. Since the given number is negative 7, Its exact opposite partner is positive 7. Therefore, x must be equal to 7. Every non-zero real number has a multiplicative inverse, also known as a reciprocal. When you multiply a number by its multiplicative inverse, the result is always 1, which is the multiplicative identity. Let's look at the formal definition. However, there is an important exception to this rule. 0 has no reciprocal. Its reciprocal cannot be defined, which mathematically means that you can never divide any number by 0. Think of multiplication as drinking a magic potion that multiplies your size by m. To return to your original size of 1, you must drink its exact antidote, which is 1 over m. Multiplying a number by its reciprocal completely neutralizes the effect, bringing you back to 1. But what about 0? 0 acts like a mathematical black hole. Once you multiply any number by 0, it gets swallowed and crushed into 0. Because the original information is completely destroyed, there is no antidote or reciprocal that can ever bring it back. This is why you cannot divide by 0. Let's test our knowledge with a new quiz. Solve for y in the following equation. 2 over 3 times y equals 1. At the same time, think about what the reciprocal of 0 would be if it exists. Let's see the questions. Here is the solution. For question 1, when a number is multiplied by its reciprocal, the result is 1. The reciprocal of 2 over 3 is obtained by flipping the fraction, which gives us 3 over 2. For question 2, as we learned before, 0 has no reciprocal because you cannot divide by 0. Every real number can be found on the number line, whether it is rational or irrational. There is a perfect one-to-one correspondence between the real numbers and the points on the line. Every point represents exactly one real number. The numbers to the left of 0 are all negative, which means they are less than 0. The numbers to the right of 0 are positive, and they are greater than 0. Remember, 0 itself is neither negative nor positive. Think of the number line as a giant parking lot, where every single car represents a real number. Each car has one specific assigned parking slot, and no two cars can share the same space. This is what we call a one-to-one correspondence. Now, think of directions. If 0 is your starting point, walking east represents positive numbers, and walking west represents negative numbers. 0 itself is the center of the compass, so it doesn't face east or west. Let's test our understanding with a quiz. Consider the number line. Between which two consecutive integers can you find the negative real number negative 3.5? Think about its position relative to 0. Here is the solution. Since negative 3.5 is a negative number, we look to the left of 0. Moving left, negative 3.5 is less than negative 3, but greater than negative 4. Therefore, it lies exactly between negative 4 and negative 3. The absolute value of a number is its distance from 0 on the number line. Because distance is always positive or zero, absolute value ignores the sign and only measures the size. For example, both positive 4 and negative 4 have a distance of 4 from 0. More algebraically, the absolute value of C is defined in 3 parts. It is equal to C if C is positive, 0 if C is 0, and negative C if C is negative. Remember, negative C makes the value positive when C itself is already negative. Think of absolute value as a car's odometer. If you drive forward 4 miles, your odometer shows 4. If you drive backward 4 miles in reverse, the odometer still goes up by 4 miles, not negative 4. It only measures the total distance, completely ignoring the direction. What about the algebraic rule where the absolute value of negative C equals negative C? Think of it as a magic filter. If a positive number enters, it passes through untouched. But if a negative number enters, the filter multiplies it by another negative sign to cancel the minus, turning it back into a positive. Let's test your understanding with a quick quiz. Evaluate the following expression: the absolute value of negative 9 minus the absolute value of positive 5. Be careful with the operations outside the bars. Let's solve it. Here is the solution. First, evaluate each absolute value. The absolute value of negative 9 becomes positive 9, and the absolute value of 5 remains 5. Now, substitute these values back into the expression. 9 minus 5 gives us the final answer for. When you add two numbers with the same sign, the sum keeps that sign. Adding two positive numbers always results in a positive number. This means positive real numbers are closed under addition. Similarly, adding two negative numbers always gives a negative result, meaning negative numbers are also closed under addition. When adding numbers with opposite signs, the sign of the sum is determined by the addend with the larger absolute value. For instance, negative 5 plus 7 results in positive 2 because the absolute value of 7 is greater than negative 5. The larger size wins the sign. Think of addition as teams joining forces. When two positive numbers meet, they are in the same alliance, so they simply combine into a bigger positive team. They never leave their positive world, which means they are closed. The same goes for negative numbers. They combine into an even stronger negative team. What happens when opposite signs meet? It is like a tug of war. The positive team pulls one way, and the negative team pulls the other way. The final sign of the sum depends entirely on whichever team has more raw power, which represents the larger absolute value. The stronger side wins the sign. Let's test our understanding with a quiz. Evaluate the following addition expression: negative 12 plus 8. Pay close attention to which number has the larger absolute value before deciding the final sign. Let's solve it. Here is the solution. Since the two numbers have opposite signs, we must compare their absolute values. The absolute value of negative 12 is 12, which is greater than 8. Because the negative addend has the larger size, the final answer must be negative. 12 minus 8 gives us negative 4. When you multiply two real numbers, the sign of the product depends on the signs of the factors. Multiplying two numbers with the same sign always results in a positive product. However, multiplying two numbers with opposite signs gives a negative product. Let's look at the closure property. The set of positive real numbers is closed under multiplication because 5 times 2 equals positive 10. However, the set of negative real numbers is not closed under multiplication. Multiplying -5 and -2 results in positive 10, which leaks out of the negative set. Think of positive numbers as friends and negative numbers as enemies. The friend of my friend is my friend, so positive times positive is positive. More interestingly, the enemy of my enemy becomes my friend. This is why multiplying two negative numbers flips the result back to positive. Because the enemy of my enemy becomes a friend, the negative numbers cannot stay locked inside their own world. When two negatives multiply, they break through the wall and land in the positive world. That is why the set of negative numbers is not closed under multiplication. Let's test our understanding with a multiplication quiz. Evaluate the following expression, -4 times -6. After finding the answer, think about whether this result proves that negative real numbers are closed or not closed under multiplication. Let's look at the problem. Here is the solution. First, multiplying two negative numbers always results in a positive product. For times x is 24, so -4 times -6 gives us positive 24. Second, because the input factors were negative, but the output is positive, the result leaked out of the negative set. This directly proves that negative numbers are not closed under multiplication. Subtraction is the inverse operation of addition, defined as adding the opposite of a number. To subtract a from b, you simply add -a to b. Because subtraction is just a form of addition, and real numbers are closed under addition, they must also be closed under subtraction. However, subtraction has a key limitation. It is not commutative. This means that changing the order of the numbers changes the result. Therefore, b minus a is not equal to a minus b, except when both are equal. Think of subtraction as driving a car with a reverse gear. Instead of having a separate road for subtraction, we simply shift into reverse and push the gas pedal forward. Subtracting a is exactly the same as turning it into its opposite direction, -a, and adding it to your position. Why is subtraction not commutative? Think of putting on your socks and shoes. Putting on socks first, then shoes, works perfectly. But if you try to put on shoes first, then socks, you get a completely different, messy result. Order matters in subtraction, so switching places changes everything. Let's test our understanding with a subtraction quiz. First, rewrite and evaluate the expression 3 minus -8 by adding the additive inverse. Second, calculate -8 minus 3 and determine if changing the order gives the same result. Let's see the questions. Here is the solution. For question 1, subtracting -8 is the same as adding its opposite, which is positive 8. 3 plus 8 gives us 11. For question 2, Negative 8 minus 3 is rewritten as negative 8 plus negative 3, which equals negative 11. Since 11 is not equal to negative 11, this directly proves that subtraction is not commutative. Division is the inverse operation of multiplication, defined as multiplying by a reciprocal. To divide b by a, you simply multiply b by a inverse. The result of this division is called a quotient. Remember, the divisor can never be equal to 0. Just like subtraction, division is not commutative. Changing the order of the numbers completely changes the quotient. Therefore, a divided by b is not equal to b divided by a. Think of division as sharing a pizza. Dividing b by a is exactly the same as cutting the pizza into 1 over a size slices and then multiplying your portion by b. Dividing by a is simply multiplying by its upside-down partner, the reciprocal, 1 over a. Why is division not commutative? Imagine 6 pizzas shared among 2 people. Everyone gets 3 full pizzas. But if you switch the order, 2 pizzas shared among 6 people means everyone only gets a tiny fraction, 1/3 of a pizza. Who divides whom completely changes the result. Let's test our understanding with a division quiz. First, rewrite and evaluate the expression 4 divided by 2 over 3 by multiplying the reciprocal. Second, calculate 2 over 3 divided by 4 and check if switching the order changes the quotient. Let's look at the problems. Here is the solution. For question 1, dividing by 2 over 3 is the same as multiplying by its reciprocal, which is 3 over 2. 4 times 3 over 2 gives us 6. For question 2, 2 over 3 divided by 4 is rewritten as 2 over 3 times 1 over 4, which equals 1 over 6. Since 6 is not equal to 1 over 6, division is not commutative. If you want to write an expression 4, add 5 and 4, then multiply the answer by 3. Writing 5 plus 4 times 3 causes confusion. Depending on what you do first, you get completely different answers, 27 or 17. To make the calculation clear, we use grouping symbols. By putting parentheses around 5 plus 4, anyone can see that addition must be done first. This gives us the unique and correct answer, 27. Now, let's test what we've learned with a quick quiz. Look at these 2 expressions. They have the exact same numbers, but the grouping symbols are in different places. Evaluate both expressions and see how the parenthesized group changes the final answer. Let's look at the solutions. For question 1, the parentheses tell us to add 6 and 4 first, which gives us 10. Then, multiplying 2 by 10 gives 20. For question 2, there are no parentheses, so we follow the standard order of operations and multiply 2 by 6 first to get 12. Adding 4 gives us 16. As you can see, parentheses change the order, and the order matters. There are specific rules about what to evaluate first. This order of operations is used by all mathematicians, so that every mathematician in the world evaluates expressions in the same way. Let's break down the 4 rules. First, calculate expressions within grouping symbols from the innermost to the outermost. Second, calculate expressions involving exponents. Third, Do all multiplication and division from left to right. Lastly, do any addition or subtraction, also from left to right. Let's imagine a huge music concert. Think of mathematical operations as people waiting to enter the concert hall. Some people have special passes to get in first. First, grouping symbols are the VIP guests hidden inside private lounges. They go first. Second, exponents are the VIP ticket holders who cut the main line. Third, multiplication and division are regular ticket holders standing side by side. Lastly, addition and subtraction are the economy pass holders who must wait. Now let's test your skills with a challenge. Evaluate this expression using our concert rules. Remember who gets the VIP access first. Pause the video if you need a moment to solve it yourself. Let's solve it together. Step 1, we have grouping symbols. The VIP lounge guests inside the parentheses go first, so 2 plus 4 gives 6. Step 2, we multiply 3 by 6 to get 18. Finally, step 3, we subtract 5 from 18. Our final answer is 13. Great job! Today, we are learning about commutative laws. It means the order doesn't matter. For addition, a plus b is equal to b plus a. The same is true for multiplication. A times b equals b times a. As you can see in the examples, 2 plus 3 equals 3 plus 2. Let's visualize this with a simple analogy. Imagine putting fruits into a basket. If you put 2 red apples first and then 3 green apples, or if you put 3 green apples first and then 2 red apples, the total amount of fruits in the basket is exactly the same. The switching of the order changed nothing. Now let's test your understanding of the commutative law. Look at this multiplication expression. 4 times 7 equals 28. Based on the commutative property, fill in the blank to complete the equation. Think about how the numbers swap their places. Let's solve it together. The commutative property states that for multiplication, the order of the numbers does not change the final result. Since 4 times 7 equals 28, swapping the order tells us that 7 times 4 must also equal 28. Therefore, the missing number in the blank is 7. Excellent job! Next, we have the associative laws. Addition and multiplication are binary operations, meaning we can only group 2 numbers at a time. However, it doesn't matter which 2 you group first. For addition, open parenthesis a plus b close parenthesis plus c equals a plus open parenthesis b plus c close parenthesis. The same logic applies to multiplication as well. Let's visualize this with a train analogy. Imagine connecting 3 separate train cars, red, green, and blue. In case 1, you connect the red and green cars first, then attach the blue car. In case 2, you couple the green and blue cars first, then connect the red car at the front. Look at the final result. Either way, you get the exact same long train. How you group them makes no difference. Now, let's test your understanding of the associative law with a challenge. Look at this expression, open parenthesis 47 plus 25 close parenthesis plus 75. Adding 47 and 25 first might be tricky. Use the associative property to regroup the numbers and make this calculation much easier. Pause the video and try it yourself. Let's solve it together. According to the associative law, we can group numbers any way we want. Instead of adding 47 and 25 first, we can move the parentheses to group 25 and 75 together. 25 plus 75 gives us a clean 100. Finally, adding 47 to 100 gives our final answer, 147. See how much easier that was? Finally, we have the distributive laws. This law defines how multiplication and addition combine together. When you multiply a factor outside by a sum inside the parentheses, it multiplies every single term inside. Therefore, a times open parenthesis b plus c close parenthesis equals a times b plus a times c. Let's visualize this with a gift delivery analogy. Imagine a house containing one person inside a circle room and another inside a triangle room. A delivery manager, represented by the square outside, brings special items. The manager outside must deliver the item to every single person inside the house. So, the circle person gets an item and the triangle person also gets an item. Everyone gets a share equally. Now, let's test your skills with the distributive law challenge. Evaluate this expression. 6 times open parenthesis 10 plus 2 close parenthesis. Instead of calculating inside the parentheses first, apply the distributive property to multiply 6 out to both terms inside. Pause the video and try it now. Let's solve it step by step. The distributive law tells us that the factor outside multiplies every term inside the house. Step 1, we multiply 6 by 10, which gives 60. Step 2, we multiply 6 by 2, which gives 12. Finally, step 3, we add 60 and 12 together. Our final answer is 72. Fantastic job!